Yeah, welcome everyone to day 2. I've really been enjoying these talks. I was going to say thanks for inviting me. Thanks for originally inviting me to help co-convene. So we study climate informatics, given the changing climate that we've been seeing and extreme events, megastorms, heat waves resulting in wildfire and drought, and their effects on communities and ecosystems. And machine learning is based on the vision that, climate informatics is based on the vision that machine learning can shed light on climate change, which is also the vision of why a lot of you are here and working in this field. And we have critical mass on bringing, community building around climate informatics, dating back at least to the first conference, which we actually held in New York, and then, went to Boulder for many years and then went international to Paris. Then we had a year virtually during COVID. I've been plugging KITP in some of my other talks. And then the next climate informatics event is going to be in May in Asheville, North Carolina. We also now have a journal that is more broadly applicable, and everyone in this room is welcome to submit. A lot of people in climate informatics are involved in the journal, but it's broader than just climate. And 6 years ago, trying to motivate machine learners at NeurIPS to work in this area, Arindam Banerjee and I tried to break up the areas, break it down into areas where machine learning could be needed. I guess we haven't really had paleo talks yet here, but the climate reconstruction is this big, sparse, spatiotemporal missing data problem where we have, temperature proxies going really far back into time, but only in certain locations where we happen to have physical or biological proxies. And we need to know past climates to put current climates into perspective. In green are areas that my lab has worked on, and I'm not going to talk about all of them. I will talk about downscaling today. I will not talk about a whole thrust we did on taking an ensemble of models, whether it's from perturbing a parameter inside the model or perturbing the initial conditions, or these ensembles of opportunity like the models from all different countries that inform the IPCC, and then using AI plus observations to essentially do some sort of fancy data assimilation to adaptively robustify your ensemble prediction. More generally, as Rose and others have mentioned, the exciting area in terms of this for machine learners is that the data is spatiotemporal. We heard a little bit from Christian around self-supervision when you have spatiotemporal data and how do you design pretext tasks. But anyway, we have these dependencies and non-stationarity. So non-stationarity over space and time is something that my group has pushed a lot. And then we've also started contributing a bit around extremes. But again, this was how we broke it up 6 years ago. And we've seen, even just in the space of the beginning of the workshop, a lot of other areas where ML can have an impact, and ML broadly defined. So yes, deep learning, also other areas. So some of our lines of work were 100% with online learning. But I am going to focus on deep learning today. The twist I'm going to take is unsupervised deep learning. In hindsight, I probably should have gone before Christian, because I'm going to go at a more introductory level. But it was great with Christian's talk. We saw some examples of designing free text tasks. So I'm going to talk about unsupervised learning, including in a semi-supervised pipeline, and self-supervision a bit in these 2 case studies, avalanche detection and downscaling of temperature and precipitation. So to sort of front load one of the technical messages, I'll say this for people that do feel like they understand supervised deep learning, at least at this level. But if you don't have the same background. What's great about these multidisciplinary conferences is that people have all different trainings and you're an expert in something else. That's completely fine. We'll get into it in the case studies. But if you are thinking about supervised deep learning, whatever your network architecture is, let's call your network applied to an input vector or field or tensor as f of w operating on x, where w are all your network parameters that are going to be fit from data. Okay, then you learn the network, fit the parameters from data by minimizing some loss function. So when the data is labeled, that's a supervised setting. So that means that given an input x, we had a desired ground truth label y, or a desired output. And so then the prediction loss function is just something that compares the output of the network to y, generally trying to draw it closer. And then you're going to do some version of sort of a noisy gradient descent on your loss. And then what we call back propagation is taking my gradient step on the loss computed on the current data point, and then figuring out, using the chain rule, how to propagate back the individual steps I need to take in each of my parameters to update and to minimize my loss and get closer to the the process that generated these x's and y's. So if you buy that, then what do you do when you want to write down an objective function, but you don't have these labels y? And hopefully this should free you up to work in domains where you don't have data conveniently labeled for some supervised learning task. Because it's actually just as simple as writing down a loss function that doesn't depend on some extraneous y, which means it could depend on the output of the network still, which now I'll call x hat. I'm still have some architecture with all my parameters, and this is my input. I just can't have a y, like some external label that is supposed to go with x in my loss, but I can certainly make my loss a function of, say, the input of the network. Okay. If you do that, then you're still going to do gradient descent now on this loss and use the chain rule to propagate back your updates to every network parameter. Okay. So for those of you to whom that technical part made sense, the point is that you don't need a label. All the architectures, will still be valid in the unsupervised case, assuming you can write down a loss function that only depends on the network's input and output. And I will also put a sidebar. I'm not going to talk about clustering, but what's very cool when you can now consider the whole training data set or maybe mini batches is that many clustering objectives can be used here. And then where there had been this whole literature that I also have contributed on approximation algorithms for clustering in the non-deep learning setting, you can just write down the objective function that you want to optimize. And there are papers such as ClusterNet that are essentially doing spectral clustering without the spectral clustering, just doing gradient descent on the appropriate clustering objective. So that's a sidebar because I'm mostly going to talk about probably what's more relevant to this domain, although clustering can be useful, which is around automatic feature extraction, embedding, dimensionality reduction, where we're going to consider how you would do that in an unsupervised setting. Okay, so for those that took a break during that part, you can pay attention to the case studies again. Hopefully this will be explained more intuitively. So I'm going to talk about avalanche detection. So avalanche detection, that ultimately the detection part has to be a classification. So that is going to be supervised. So I'm going to have an entire pipeline that is semi-supervised, but I'm going to lean in heavily to the unsupervised part. And this is sort of along the lines of, along a line of work where we're working on extremes. I think maybe the most interesting or unorthodox idea here was the first bullet where we did topic modeling from text mining to, in an unsupervised way, detect diverse multivariate extreme events from multivariate data in a very soft and probabilistic way. But anyway, so this avalanche work was led by my postdoc and student. Sophie's now at IRD in Grenoble. And I think there might be some correlation to climate change. I'm not going to claim it. That said, we can also certainly study climate change impacts by looking at detection of avalanche. But seen as a machine learning problem, this is interesting from the perspective of severe class imbalance. So this is true anytime you have rare events, and severe limitations on the amount of labeled data that you can have. So our labeled data is literally ground truth. It's collected on the ground by humans trekking into certain avalanche corridors in France. That ground survey was from Météo France, our collaborators. And then we had, as much synthetic aperture radiation data from Sentinel missions as we wanted. And we didn't have any in-between product. You might imagine SAR imagery that had then been segmented by human experts looking at the imagery. We did not have that, and our colleagues felt that it was hard, even for experts, to have much skill in that task. So we have some finite number of corridors where humans have measured whether avalanche deposits fell, and then as much SAR data of these snowy avalanche corridors as you want. And so the kind of supervised wrapper is anomaly detection, where we have to classify whether we've seen an anomaly or not. And a sort of obvious way to use unsupervised learning would be to learn in an unsupervised way a model of the negative class. So patches that don't have avalanche deposits, say fit a VAE on those. And then for that supervised wrapper, we need some rule to classify avalanche or not avalanche. So just for the purpose of building intuition, if you've trained on the negative examples, then when an unlabeled example comes in, you want to see how well the trained model can reconstruct it. And if it does poorly, then maybe this is an anomaly, maybe this is an avalanche. So this addresses the rare event aspect of the ML problem, but it doesn't really address the fact that we have very limited labeled data. Because let's think about where the labeled data is needed. So certainly step 3, because we're going to do classification, we are going to need some labeled data to tune a hyperparameter, which is the threshold on reconstruction error, above which we'll say that we've seen an anomaly. But if you think about it, there's also a bottleneck of supervision between 1 and 2, because somehow we were going to sort out and only feed negative image patches to the VAE training procedure, which means we already had to waste some of our labeled ground truth survey to actually label those images. Okay, so the twist that we propose is replace 2 with just skipping any supervision between 1 and 2 and just learning a VAE on satellite data where we haven't checked whether it has avalanches or no avalanches. So just the SAR data. Okay, so again, working from the punchline backwards, now I'm going to talk a little bit about what a VAE is. And also to talk about pretext tasks. So Christian certainly referred to pretext tasks. So certainly you could have a task where you input images and then try to reconstruct them exactly. And then because you're learning parameters in these network blocks. You might not actually exactly reconstruct it. We call that a pretext task because that's a really useless machine. Who wants basically a shoddy version of the identity function? Why would we bother learning that? Well, it's a pretext because after we train on a lot of images from this distribution, we're hoping that we can basically, in an unsupervised way, extract a lower dimensional representation or extract features from that data. So the whole idea of pretext tasks is, especially in unsupervised learning, where my loss can only depend on the input or the output of the network, you can write down some loss, but if it's a loss that just pushes the input to be close to the output, that's not a very interesting task. What's interesting is what we can do with it afterwards, that the learned features would be interesting. So vanilla autoencoder is something like this. When you go from a higher dimensional space and push it through a lower dimensional bottleneck, that's called a dense autoencoder. And if you have really high dimensional data and you want a compressed representation, you're probably going to want to do that. Just a quick note, coming out of cognitive science and also neuroscience in other animals, there's evidence that in, say, the human visual system and certainly in the olfactory system of the fruit fly, we are actually projecting to a higher dimension. That's called a wide autoencoder, which is to then represent our data more sparsely, so that if we perceive different signals out in the world, we can separate them well. Okay, but in our case, probably we want to do embedding. And then when people talk, so that's the idea of an autoencoder. When people say VAE, variational is used to describe how you would fit an autoencoder that instead of just learning a latent representation will now learn a distribution over latent representations. And the classic example is you'll start with some isotropic Gaussian, but then eventually learn some kind of covariant structure and mean vector in the process of estimating the parameters. If you're not happy with Gaussians, stay tuned to the rest of the talk when we talk about normalizing flows. Okay, so the sort of first pipeline that I gave that was sort of a straw man said that, okay, I have to label the images using the ground truth survey, and then I take the negative images and fully train an autoencoder. So, I'm fitting parameters here, 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 and there. The version we want to replace that with is skip the supervision. Just take image patches from your SAR data, so you don't know, whether it has avalanches in it, and then from there train an autoencoder. Whichever version of that step 2 that you do, you still have to do the tuning of the hyperparameter that allows you to do supervised learning. So how does tuning work? You have a labeled validation set. So for every image patch, there's a known label. Was there avalanche deposits in there or not? You just feed the image through the trained autoencoder. You're going to get some output. You can compute that reconstruction error, that loss comparing input to output. And then in green is the threshold that you're tuning. You want to choose the value such that most of the guys labeled 1 in your set are above that threshold on reconstruction, and most labeled 0 are below that threshold. That's why you have a labeled validation set. And so then you've set your threshold. Then how does the anomaly detection pipeline come in, work? So an unlabeled image comes in, you send it through the trained VAE. You compare the reconstruction error between output and input to the tuned threshold, and then that's how you label whether it's an avalanche or not.
Sorry.
Yeah.
Idea basically that avalanches are so rare that the VAE doesn't really learn them. That's sort of the idea.
Can you repeat the question in the microphone, because we can't hear it?
Oh yeah. He was saying, I think he was saying, is the idea of our final algorithm, not the straw man algorithm, that because avalanches are so rare, they were not modeled very well by the VAE to begin with. That is something to think about. We have a different interpretation that I'll talk about in the results, but that's a good sort of devil's advocate approach that we'll have to eventually disprove. Cool. So the Météo France collaborators were coming not from machine learning. They had developed techniques where you could look at the SAR bands and threshold some things. It was not a learned method, and they weren't happy with it because you'd get these like spurious mini house-sized avalanches in town. They, you're sort of unlikely to get nicely connected avalanches that way. And in general, it was a really hard task, even for that thresholding method. And in previous work, we tried a supervised deep learning method. We heard a lot about convolutional neural networks yesterday. But because it was supervised, then we have the class imbalance problem. And there's a few ways to address that, one of which is you have an artificially balanced data set, which means you have to generally use much less data. So both the semi-supervised pipelines, so the whole pipeline is semi-supervised. This just indicates whether the VAE required any supervision before learning it between these two. Both of them definitely got a lift above the supervised version. And we, I guess, in some sense, surprisingly got a significant lift by learning the VAE 100% on unlabeled data. So first off, you're learning off of more total data points. And for us, that generally helps with generalization and reducing overfitting. But if you think about it, you're learning with noisier, messier data in the second case, because the data points that you've added back now, probably have some avalanche deposits in them. But I think the key thing to note is sort of the order in which things are done, which is that in any good machine learning or computer vision paper, when you look in the results section, each method gets to optimally tune their hyperparameters independently from the other methods to have the best hyperparameters that they can with respect to the labeled validation set, which is different from the final test set results. So the value of the threshold is probably going to be different when you have much more noise in your training data than in the other case. But because this was trained on more data and also more fully explored the feature space, we view that as a form of regularization, which in general helps generalization performance. And then this result also held up for things like ROC curves. So keeping mindful of the time, I think I'll conclude on this one and then get into the downscaling via normalizing flows. So let me mention the outlook here and then take any more questions before I go to the other project. So take home for machine learners is that if you only have a limited amount of ground truth data, and we've showed it at least in the case of rare events, if you ultimately need to do something supervised, you're going to have a semi-supervised pipeline, but you should lean as much as you can on unsupervised learning. And ideally, that labeled data set is only used to make a validation set to tune the hyperparameters of the sort of supervised wrapper to your pipeline. Okay. Also, this relates to the idea of virtual sensors. I've heard that, NOAA, for reasons of it being too expensive to run radar everywhere, would like to take different satellite imagery, train in places that you have radar, sort of these virtual proxies of radar. This is very similar. The virtual sensor was the people trekking into the mountain. And if we can sort of replace having to do that by learning a model between satellite and the ground truth, then we can do that. And then, of course, this is avalanche detection. Of course, avalanche forecasting would also be very interesting. So, okay, I'm going to transition to the next topic. And just, this would be a good time for questions.
Could could you just say a couple words about the nature of the avalanche data that you fed in? I think you said it was satellite based, but like, were you flattening into a 1D vector before feeding into the variational autoencoder? And great talk so far.
Thanks. It was synthetic aperture radiation, and we were taking 64 by 64 by 4 image pixels. And so I think the 4 channels were, oops, do I have it? We used backscatter coefficients and slope and angle. And we used 2 backscatter coefficients per location because we also used the one from the previous, I guess, 6 days. Oh, actually, there was some issue as to whether we did the different missions separately or included them. But yeah, so for further details, I can put you in touch with the lead student on that. Thanks. And I think these folks at Météo France, they want to still work on this, and if anyone's interested, I can put you in touch.
Quick other question.
Yeah.
Are you including time?
Sorry?
Are you including time?
In this one, we are not, but it actually, so that's a really interesting point. When I talked about the different orbits, I think like they might have a 6-day coverage. And so if you're only looking at like between the two, each one has 12-day and then they're overleaved. So we were first thinking, are we trying to, like, how new do we need the avalanche to be? And yeah, it is really hard to know if the avalanche fell within the last 6 days versus 12 days or a month. And we ended up kind of throwing that out the window for this proof of concept.
Yeah, I imagine in the Alps, like the temperatures can change a lot. And
oh, whether we took time as a feature for training.
No, I meant, so what you were just saying, like if you take them a month apart, then that can really make a big difference.
Yeah, I think ultimately we did not try to show how new the deposits were. So,
thank you.
Cool. So now for something completely different, although it's kind of related. Unsupervised learning for downscaling. And we did examples of this for temperature and precipitation. There's no reason this couldn't be done for any other field. And we did spatial downscaling. You could also do temporal downscaling. And that's me talking to the domain scientists. To the AI people, you would generally think of this as super resolution. So we say up in AI and you guys say down. So, and this is this is an unsupervised task as opposed to the last one, but I'm going to touch on self-supervision for why it works so well. So Brian Gronke did his master's thesis in CS in our department, and he's now he got radicalized around climate, and now he's doing his PhD in Alfred Wegener in Potsdam. And first, he was at Jupiter Intelligence for a summer internship and tried some super resolution techniques from computer vision that had been applied in this literature and didn't get as good results as what we're going to talk about today. So just to be very clear with terminology, let's stick with, say, the climate terminology, downscaling. I have gridded data at a coarse scale, and I would like a finer scale of that same field. So I'd like, and as Christian motivated, without losing important, physical details. And our sort of ML view of the field of statistical downscaling is that we interpret it in terms of supervised learning, because there's a lot of methods where if you have a map of a variable at coarse scale and a corresponding map of the same variable at a fine scale, then you can train those methods. So we view that as, when you need paired data, we view that as labeled data. And also they provide point predictions, meaning once trained, give me a coarse grid, and I can output a finer grid. But we wanted to do generative downscaling. Wow, I think I'm really short on time. Who am I talking? Oh, Hank, how's the time?
Well, you formally have still total 50 minutes, and there were some questions already. So just go ahead. You can talk for another, say, 8-9 minutes or so.
Oh, okay. So I'll try to finish this up. Yeah. So generative downscaling. So generative is a word we use in machine learning where once the model is learned, you can sample from it. This might have been, I think, at the end of Anisha's talk, he was talking about Bayesian neural networks. So I'd like to actually be able to have an entire distribution over maps at the fine grid scale. I'd like to be able to sample both conditionally and unconditionally. So if you give me an input image at coarse scale, I should be able to conditionally sample fine scale images, or I'm going to now have a posterior distribution learned over our latent feature space that I want to be able to sample from. So the key idea of Brian's was to appeal to domain alignment coming out of unsupervised deep learning. And in particular, he used an idea called align flow and instantiated the normalizing flow with GLOW. We'll get into those details shortly, but the punchline is that it worked. And then the punchline intuition I have around that is that ultimately there was self-supervisory signal in the data that allowed it to work. So unlike the methods I talked about where you need paired maps and coarse and fine resolution, we didn't need that. You did need you needed maps at both fine and coarse resolution, but they didn't have to be paired. But ours were registered geographically over the same region of continental US, whether at coarse or fine. And since we know the underlying physical processes do depend on location, there was information sharing there that we would call sort of a self-supervisory signal. So it's as an AI person, we don't care too much where the data came from. And that's sort of demonstrated by the fact that we have lower dimensional, so finer resolution data from our simulations. So NWP WRF simulations created our fine scale. Our coarse scale was actually from our observation or reanalysis data. So it doesn't really matter. And actually this method is symmetric and cycle consistent. So you could either upscale or downscale. We did a temperature model independently from a precipitation model. But yeah, these are two different sources where often you might think that the model data would give you the coarse grid, but it just so happened that we used 1 degree resolution from reanalysis and NWP for the finer resolution. So the general idea of domain alignment is that given two random variables, if you have IID samples to their marginal distributions, then you want to learn this mapping F that's invertible. So if I have samples from the prior of X, I can approximate the prior of Y by applying the F. And if I apply F inverse, then I can approximate the prior of X from samples from the prior of Y. So our X and Y are going to be our coarse resolution and fine resolution. And so we don't ever need samples from the joint. We don't need paired examples, but we do need IID access or data sampled IID from their marginals. And also if you were looking at like earlier slides where X was example, Y is label, these are just two different random variables. Ideally, what we'd want is the joint, right? And so the idea of a line flow is to make a conditional independence assumption. Let's assume the two domains, coarse and fine, are conditionally independent given some shared latent space, so indicated by this variable Z. And then, of course, the full joint would factor as follows, and then we just integrate out over the prior to get the joint over X and Y. How is this implemented? So we're going to learn these actually distributions at the coarse scale given the latent space and fine scale given the latent space via normalizing flows. And then again, no pairing of these examples is needed. So normalizing flows. Go back to what we were talking about, a variational autoencoder where we learn a Gaussian over the latent space. You can actually start with a Gaussian or something simple and then apply a series of transformations. And the idea is, as long as these transformations are invertible, it makes inference pretty easy because you can get your inference back from your simple prior. And also you get the cycle consistency for free where you can map both directions. And then the learning process will fit parameters of these functions that you compose. So the kind of well-known variation normalizing flow paper use certain normalizing flows. We're using a different one that doesn't have these visualizations, but these visualizations are pretty. So the punchline is that we're going to learn a normalizing flow between this joint latent space Z and one resolution, and similarly for the other. That's what this whole aligned flow architecture does. The only learnable parameters of interest are these flows, which are a bunch of parameters so that you can get these invertible mappings between coarse resolution and latent, fine resolution and latent, and implementation detail. The latent we used, we represented at the same dimension as the high resolution. So we also represented the low resolution data that way, which means we just upsampled to fill in neighbors with adding as little information as possible. So we can do a sanity check that we're not doing too much worse by using unsupervised learning compared to supervised learning, both a CNN method and like sort of a standard downscaling approach. In Brian's thesis, he also looked at all the ClimDex indices and things were in the right ranges. We don't do better than it because those are supervised techniques, but those all require paired data. And so if you don't have paired data, then you couldn't even run their methods. And then these are judged on point predictions, but sort of the richness of probabilistic predictions will show qualitatively. So I can take a coarse scaled precipitation map. And for this test, I'll take a paired set where there's this fine-grained image here that was paired. But that's not given, the middle image is not given to the learning algorithm. So the maximum likelihood prediction would be here. And then you could also just sample conditionally on this input as many times as you want. And so now you can give tons of fine-grained precipitation maps to your domain scientists and ask if it looks realistic. And then we can also do some of these interpretability studies that are cropping up in machine learning, such as a temporal interpolation. So say we have fine scaled maps at 2 different times in our, in the data that we've been using. We can map them to the latent space. We can certainly generate coarse grid maps. So this is actually, I guess, upscaling. And then we can walk in the latent space and at each point in the latent space generate coarse and fine grid images. And there's a whole literature now in machine learning on how to do that walk, to do a geodesic with respect to the learn posterior, but do it efficiently. So yeah, I think I'll close. Just for the purposes of spurring discussion, I want to mention some challenges. I'll just be brief here. So the first part of the talk, actually, the whole talk was talking about unsupervised learning because we don't have a lot of labeled data. The first part of the talk talked about class imbalance. And more interestingly, I think both Christian's talk and also yesterday Rose's talk relates to what we're thinking about in our group of how do you design pretext tasks that learn features that are embedded in both space and time. There's this Google paper coming out in CVPR 2021 that sort of breaks it down and says people would study video in an unsupervised way and either learn temporal features or spatial features. They had this whole great thesis in the paper, and then their method, like first you learn spatial features and then you learn temporal features. I've seen non-deep techniques out in the climate literature that are learning in both space and time. Also, we don't have a counterfactual Earth. We don't have a very long time series, but we're starting to have super high resolution spatial data. Can we somehow use that as a proxy? We have a lot more data diversity and granularity over space. Can we substitute that for the time histories that we don't have? If you're interested in non-stationarity, we've done a lot around spatiotemporal non-stationarity and learning methods. And then we're also really interested in interpretability. I love all these papers cropping up about GANs, but it's open even in AI. How do you even evaluate whether the distribution of images that your GAN generates is faithful to reality? And that's quite open. So thanks.
Yeah, thank you very much, Claire, for this very nice overview of these methods. And there's still time for 1 or 2 questions.
Also put some resources.
From the audience, maybe first.
Thanks, Claire. Great work and great talk. Both regarding the VAE work and also here, do you look at the latent representation or the encoded layers, and is there use to interpret them on why the network is learning what it is? Like, does it inform on the physics of the system, or why is it detecting an avalanche? Or
I think we could make a big start on that in the next 7 weeks. This is the question that I get all the time. And, you know, an ML person that doesn't want to incorporate domain knowledge will say, oh, look, we can get at interpretability by like looking at and walking through latent space in a sensible way across the posterior, and then seeing, you know, what this continuum looks like. Like if I go from Brad Pitt to Angelina Jolie, do I get human faces everywhere in between? That's kind of state of art in ML interpretability. But no, I would love to develop. I mean, I feel like, yeah, per problem, you and I could sit and say, hey, is that a good precipitation map? But I think on the AI side, you know, interpretability and automated methods to generate interpretations is really interesting and could be like a whole working group for this program.
okay, thanks.
I see a question online from Sebastian Hoffman.
Yeah, hello, thanks for the great talk. I was wondering, you mentioned domain alignment, right? And I was wondering if this is somehow maybe related to CycleGAN, if you're familiar with the method.
Yeah, so AlignFlow did cite CycleGAN, and it does make use of an adversarial loss in addition to regularizers as to how far your learned flow gets from the simple prior. But I think there's a few issues. So with things like CycleGAN, you have to write down a cycle consistent loss. This, because it's using only flows, by design, everything is cycle consistent because you can, you have these bijections once you compose your flow. I guess the other issue around GANs is convergence time, right, to fit parameters, and then also vanishing gradients. But yes, it is along those lines of work, and check the whole domain alignment literature.
Thank you very much.
Yeah, and great work to you guys as well.
Then there's a next question online from Elizabeth Barnes.
Hi, Claire. Thank you for your talk. I thought the first half just like blew me away. I think this is amazing. It makes so much sense. And I'm constantly trying to think of ways to do more unsupervised learning whenever possible. I just think this is awesome. And maybe this is standard in your area, but from a domain scientist, I just think this is so cool and has so many applications for how you use the VAE and really only use the labeled data, really, if you will, sparingly for getting that threshold. And it makes a lot of sense. And so I'm just wondering, have you guys thought about, or are you actively pursuing this approach for things like climate extremes? Like, I mean, I can just imagine training on pre-industrial control runs of climate models and using this exact approach to go looking into the future.
No, yeah, that's a good point. It was sort of like kind of this niche that we're building for publications, because I think ML people and computer vision people did have sort of an aha moment, but it was just a twist or an unorthodox really application. And so ultimately, we published it in Climate Informatics. But yeah, when I get back to Colorado, I'd love to like talk about other extreme events where you can use your models for as much unsupervised data as you want, and have some labeled data. So that's exciting.
Yeah. Just thank you. This is great. So thank you.
Awesome. Thanks.
Well, that's a good moment to end this morning session. So thank you very much, Claire and Jacob, for the nice talks, and all the other speakers also again.